start off with Unit 4. The heading is Groups and Periods in the Periodic Table. Now, we have done the periodic table in grade 8 and grade 9, and those things basically stay the same. They don't change from year to year. We just sort of learn a little bit extra stuff with it. Now, the first part, they refer to the relationship between groups and periods. Now, the groups are the vertical columns on the periodic table, and we distinguish 8 groups. Group 1, 2, 3, 4, 5, 6, 7, 8 groups, all right? We normally number them with Roman numerals. Group 8 is also known as Group 0, and we'll explain the reason for that in a moment. The group number, you should know this at this point, tells us how many outer shell electrons an element has. Now, why do we need to know how many outer shell electrons an element has? Well, we need to know that so that we can deduce the number of bonding places. And why do we want to know the number of bonding places? One of the next modules that we are going to do is chemical bonding. All right. So, the group number tells us how many outer shell electrons. Remember, bonding occurs with outer shell electrons, not the inner shell electrons. Okay, so the outermost shell of electrons is the one that is involved in chemical bonds. Next thing here, elements within groups have similar properties and very often tend to react in similar ways. Now, a little bit further on, we will go and have a look at group 1 elements and their reactions with different substances, and we will see how they react. All right. The periods are the horizontal rows. The first period contains 2 elements, hydrogen and helium. Then the next period contains, well, at this point, 8 elements, and the next one, 8 elements, and then the next one contains more than 8. But don't worry about that, all right? So, we say the periods then are the horizontal rows, and the period number tells me how many shells that atom has. So if I stick my finger onto an element on the periodic table, this element, how many outer shell electrons does it have? It lies in group 3. So it's got 3 electrons in its outer shell, but how many shells does it have? 1, 2, 3, 4, 5 shells. You follow? Okay. The next thing then, I talk about noble gas structure. Now the group number corresponds with the number of electrons in the outer shell of an element. Now group 8 elements, group 8, also known as group 0, has got filled outer shells. What can you deduce from having filled outer shells? There will be no bonding places. All right. So they will not bond. They are stable. All right. Helium only has 1 shell. The first shell we know can only hold 2 electrons. Remember the model that we do? 2 electrons, 8, etc. All right. After helium, we get neon. It has 2 shells. So the first shell will have 2 electrons, and the second shell will have 8 electrons, filling it up. Okay? Argon has 3 shells. The first shell will have 2 electrons, the second 8, the third 8. Krypton has 4 shells. The first shell will have 2, the second 8, the third 8, the fourth 8. All right. The outer shell holding 8 electrons. Noble gases, therefore, have filled outer shells. Therefore, they are inert. What does that mean? They don't want to react. All right. All the atoms from groups 1 to 7 will lose, gain, or share electrons in their outer shells. Okay, in order to attain a so-called noble gas structure. What's the noble gas structure? 8 electrons in the outermost shell. any element wants to go to the most stable state. That is why it forms bonds, because usually the compound is more stable than the separate elements. What makes them more stable is when they have bonded, they have filled up the outer shells, either by emptying the outer shell, so the shell that is left now has got 8 electrons in it, it's a full shell, or by gaining electrons, in other words, taking in electrons, filling up the shell to 8. Can it take up more than 8 in total? No. Okay, there is only place for 8. Another way then is to share the electrons, and we will have a look at that during bonding. Yeah. Which atom is in group 3? Now what determines the group number of the element? The outer shell electrons. So, go and look at the picture. They've given you a count. Which one has got 3 outer shell electrons? It is D. The next question, 2. Which arrangement of electrons in the atom show an unreactive element? When is an element unreactive? When it has a filled outer shell. So either 2 if it's helium, or 8 if it's any of the others. So it would be element D288 would be a noble gas structure, unreactive. Question 3. All elements in group 4 of the periodic table have the same number of protons and neutrons. Is that true? No, it's got nothing to do with protons and neutrons. B will have the same number of electrons in their outer shell. Yes, people, the group number tells me how many electrons there are in the outer shell. So C and D then would also be incorrect. They will have similar chemical properties. Number 4, the electron structure of element X is 285. Let's quickly have a look. 285. So now they ask, what is the group number of element X? Now the group number tells me how many outer shell electrons there are, so it has to be in group 5. And the next question, what is the period number? Well, I count how many shells there are. We have 1, 2, 3 shells. Therefore, period 3. Do you understand? Okay. I don't think there's anything new or excessively difficult on that part. Okay, so we are going to carry on with Unit 5. The heading simply says periodicity. The next section, they refer to periodicity, and they simply say periodicity refers to repeating patterns in the properties of elements in the periodic table. Okay, here we have a table with the elements of period 3. Here we have a periodic table. Which elements lie in period 3? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Alright. And now what they've gone and listed the phase. Solids, gas. Alright. Boiling point. Look at the boiling point. It's quite interesting. It goes up, and then suddenly down. What happens over here? It's the division between metals and non-metals. So if I asked you to explain something in terms about the trend in the boiling point of the period 3 elements, what can you say? It tends to increase as we go along the metals. What do we know about the elements that lie on the step? Properties that overlap with metals and non-metals. So silicon, even though it's a non-metal, it has a very high boiling point. Alright. And then we could say when it switches to non-metals, phosphorus, sulfur, chlorine, we find that there is a decrease in the boiling point. And that's got, yes, because it's a gas at room temperature, no? Chlorine is also a gas at room temperature. So they tell us, as we move from left to right across period 3, what happens? We have metals. Silicon, which lies on the step, we call them metalloids, and then we get non-metals. Okay? They say the atomic number increases. Now, what's the atomic number? It is the number of protons. Now, where do we find the protons? in the nucleus. Now, remember, all of these elements, they have the same number of shells. Okay? The nucleus is positive. It attracts the electrons. Now, if I have a more positive nucleus, what's going to happen to the attractive force on the electrons? It's going to be stronger. Okay? But can it pull it out of its shell? No. Okay, so what we find, as we go across the periodic table, the atomic number increases. Sodium has an atomic number of 11, magnesium is 12, aluminium 13, 14, 15, 16, 17, and 18. So what happens to the nuclear charge as we go from left to right? It's increasing. Okay. Now, we also have one extra electron in that outer shell. So the negative charge is also increasing. All right? It's in the same outer shell. In other words, it's got 3 shells. We're busy with period 3. The atomic radius, the size of the atom in other words, becomes smaller as we go from left to right, because we have the stronger positive charge pulling the electrons closer. All right? Yes. The nuclear charge increases due to the extra proton. The atomic number increases. All right? There will be stronger attractive forces between the nucleus if we have something, for example, with 17 protons, let's say chlorine. It's got 17 protons and 17 electrons, and if you compare it to something with 11 protons and 11 electrons, the force over here is going to be stronger, trying to pull them in closer. So very simply, we find then that the atomic radius becomes smaller. Okay? The atomic radius, remember the model says atoms are spheres, particles. It's got a radius. So if the radius becomes smaller, yes, because it pulls the electrons in closer. Okay, yes, it's becoming smaller. Do you understand? Okay. Let's just quickly step away from the book for a moment. Just here, listen to what I have to say. In general, what do metals do? Now, we were actually working from last year. Do they gain or lose electrons? They tend to lose the electrons. Okay? What do non-metals do? They tend to gain the electrons. So, how would the atomic radius of something like sulfur compare with something like magnesium? Magnesium is going to lose its electrons. So the iron is going to have a slightly smaller radius. Yes, emptied the shell. So it's got 1 shell less. But what does sulfur do? It's going to fill up its shell, so it's going to be bigger. So we would expect the ions of sulfur also to be bigger than the ions of magnesium. All right, but you don't have to worry too much about that now. Just know atomic radius will become smaller due to stronger nuclear attraction. We draw it like this. If I have the periodic table over here, we say the atomic radius, it's going to decrease from left to right. We say the atomic radius does that. You with me? What is that sign? It means smaller. Goes from big to small. So what do the atomic radii do? As we move across the periodic table from left to right, they become smaller. If I ask you to explain why do they become smaller? The nuclear charge becomes more, +1, as we move across from left to right. And it has a stronger force of attraction, trying to pull them in closer. They say there's another trend in melting and boiling point. They say melting and boiling points in periods 2 and 3. So here we have period 3 tend to increase among the metals. Okay, so the more protons there are, the stronger the Coulomb forces. So the higher we find the melting and boiling points for metals. The forces, yes, the higher the melting and boiling point. And then they say up to group 4, so where we have 1, 2, 3, 4, here's group 4, what happens? And then they tend to decrease towards group 8. All right, and that's got to do with the non-metallic characteristic. When the non-metals bond and form molecules, what forces do we have between molecules? Yes, molecules have weak van der Waals forces, but metals are positive atomic rests in a sea of delocalized electrons. Can you remember that? Or you've not done that? Oh, goodness me, you've not done bonding of metals. Okay, all right, we will get to that then. I am a bit going ahead of myself. Okay, so just remember then, melting and boiling points for both period 2 and 3 tend to increase from left to right, but once again, when we reach the non-metals, then there's a tendency to decrease, and that's got to do with the forces between the particles. Between the non-metal particles, the forces tend to be weaker. Between the metal particles, the forces tend to be stronger. Are you okay with that? All right. Periodic trends in a group. What are the groups? The groups are the vertical columns. We say elements in the same group have the same number of electrons in their outer shell. This means that they will have similar chemical properties. For example, they have got 3 bonding places. So they will bond onto 3 things having a single bonding place. Do you understand? All of them will do that. Okay. When we go down a group, because the atomic radius increases as you move down a group, who can explain that? Why will the atoms become bigger as we go down with each period? There's an extra shell of electrons. Okay, so that is why the atomic radius will increase as we move down a group. So if I go back to my periodic table, what will I draw over here? Atomic radius will increase as we go from top to bottom. All right. So, why does the radius increase? There is an extra shell of electrons. It's as simple as that. Changes in reactivity. We find generally reactivity increases as you go down a group in the metals. So if we have our periodic table, if I look at metals and I had to give a wild guess, is that one more reactive or that one more reactive? Reactivity increases as we go down a group for metals. But the non-metals are the exact opposite. Their reactivities tends to decrease as we go down a group. All right. So changes, metals tend to increase and non-metals tend to decrease in reactivity. And these are just general things that you should try and remember, because later on when we do chemical reactions and they ask you how violent will this one react or how slow is the reaction, you should know little things about metals. Oh, okay, they are more reactive as we go down a group, but non-metals are less reactive as we go down the group. Okay. The check your progress, page 103. Let's quickly have a look at that one, and then we are finished for the day. Page 103. The table shows data on elements in period 3. A. Discuss the trend in reactivity and in melting points from sodium to aluminium across the 3rd period. So from sodium to aluminium, what happens to the reactivity? It is going to increase. And what's going to happen to the melting point? It is also going to increase. And then they say from phosphorus to chlorine, in other words, it's between the metals and then in the non-metals. So by the non-metals, what do we know about the reactivity? It tends to become, no, the reactivity increases. Okay? And then the melting point also tends to, or the melting point tends to decrease. Okay? The reactivity among the metals will become more over there, okay? But then from the metal to the non-metal, you'll see the reactivity is suddenly less, and then the reactivity increases again from left to right. All right.
When you watch football on GoTV, you know what you want. You want superstars.
What about that?
The biggest names in the game. And of course, the best leagues in the world. Yes, you want explosive football action. And this new football season, we're serving it to you on a shiny new platter with our revamped SuperSport channels. All you have to do is tune in and we'll make it worth it. So get and stay connected to GoTV for football worth watching. GoTV, live it, love it.
The heading in your textbooks says group properties. So we are basically going to have a look at the periodic table and the different groups of elements on the periodic table, and we are going to look at properties that have trends within the groups. Okay. If we look at group 1 elements, they form these elements. Except for hydrogen, all of the others are metals. Okay? So group 1, they are commonly known as the alkali metals. Now the reason for that is they react very vigorously with water, and when they react with water, they form the metal hydroxide. For example, if I take a piece of sodium and I add it to the water, it forms sodium hydroxide. And sodium hydroxide is water soluble and it's basic. So it forms an alkaline solution. So we call them alkali metals, all of them. Just like any other metal, they are shiny, malleable, ductile, sonorous, good conductors of both heat and electricity. Those are common metal properties. Now, except then for the common metal properties, we find that the group 1 metals are relatively soft. Usually, they've got the consistency of a brick of butter that comes out of the fridge. You need a knife, you can cut it with a knife. Okay? Now, these group 1 metals are relatively speaking soft. If I have a knife, I can cut a piece off. It's hard, but you can cut it. Okay. So we say they are in comparison to metals like copper or zinc. You can't just cut it with a knife. Alright. So we say they are relatively soft metals. You can cut them with a knife or a blade. These metals are actually quite reactive. So if you have a piece of sodium, now we store them in the laboratory underneath an oily liquid, something like paraffin or just any oily liquid. It's to prevent oxygen and water from making contact with the surface of the metal because it reacts very violently. So if you could take out a piece of sodium from the oily liquid in which it's kept, you will see that it's not nice and shiny like normal metals are. The reason is it immediately reacts with oxygen, water vapor in the air. It wants to react. It corrodes. So if you take a piece of sodium and you cut it with a knife, the newly cut surface is bright, but as you look at it, it turns dull. Okay. So newly cut surfaces will be bright and shiny, but just for a very short period of time, because then it has lost its electrons on the surface and it is dull. They are very reactive. They are so reactive. I cannot take a piece of sodium and put it on the shelf in the laboratory because there would be a danger of it starting to burn. Sodium and potassium is even more reactive. All right? It reacts violently with oxygen and with water. Our atmosphere has got lots of oxygen in it, and in the winter there's lots of water vapor in it. All right? And the reaction is exothermic, meaning it gives off energy, and it gives off so much energy that we can see the energy as a flame. All right, it burns. So they are very reactive. If we look at them, their reactivity increases as we go from the top to the bottom. In other words, sodium is more reactive than lithium. Potassium is more reactive than sodium. Rubidium more than potassium, etc., etc. All right. Now, commonly in the laboratory, we usually have, or we could possibly have lithium, sodium, or potassium. We don't keep these because they become violently reactive. All right. They will be stored in a bottle with an oily liquid, liquid paraffin, ordinary oil, anything that won't evaporate, okay, to prevent it from making contact with oxygen or water vapor. So they are very reactive. They are stored under an oily substance to prevent the reaction with oxygen and water. They have low melting points. Now normally, if we have a look at the transition metals, you will see they have much higher melting and boiling points. Okay? So I'll come back to the properties of metals in a moment. They have low melting points. They have low densities. In actual fact, some of the group 1 metals float on water. Lithium and sodium and potassium, specifically sodium and potassium, float. If I take a block and I throw it into the water, it floats on the surface like a piece of wood. But it reacts very rapidly with the water. So if you look at it, if you take a tiny little piece, you will see that the little block of metal that you put on, it melts and it forms a little globule. And this little droplet runs around on the surface of the liquid because it's reacting with the water. All right? And as it runs on the surface, sometimes you can see a little trail in the water of a milky color. It almost looks like a little bit of smoke. But that is the sodium hydroxide that dissolves in the water. It makes it slightly milky. All right? So they then are very reactive. They have low melting points. They have low densities. Some of them will float on water. They form a white water-soluble salt. We'll have a look at the chemical reactions a little bit later on, but when sodium reacts with water, it forms sodium hydroxide plus hydrogen gas. The sodium hydroxide is water-soluble. It changes, it's an alkaline substance, so the water becomes alkaline. That's why we call them the alkali metals. Their physical properties, the ones we can see, okay? Physical properties of the group 1 metals. Usually we work with lithium, sodium, and potassium. Potassium being more reactive than lithium. Now lithium, I could store some lithium on the shelf in the laboratory. But if I left it there for a couple of months, when I walk in there again, I will have a little heap of white powder left. It's going to react with the oxygen in the air and the water vapor in the air, forming lithium oxide or lithium hydroxide. And lithium oxide or hydroxide is a white substance. All right. So I won't have my lithium eventually. So I will also, if I have lithium, I will store it in an oily liquid, although the lithium is not that reactive. All right. But sodium and potassium, you have to store them under an oily liquid. So there we just have the symbol. There's nothing new. Look at the melting points and the boiling points. Can you see, as we go down the group, from lithium to sodium to potassium, etc., as we go down, the melting point decreases. General properties you need to know. You don't need to remember specific melting and boiling points, but you need to know group 1 elements become more reactive as you move down. Melting and boiling points decrease. Density increases. Yeah. Okay. General trends. Usually they will give you the values, and they will say discuss the trend. Okay, so in general then, melting point, boiling point decreases as we go down a group. Density tends to increase as we go down the group. So eventually we find that then as we move down this group, these ones are less dense, but maybe over here they will be more dense than water and they will sink. They say the reactivity increases down the group. That you should know. In general, all metals reactivities in the groups increase as you go down. And in general, non-metals tend to decrease in reactivity as you go down. So that's like a general rule you should remember. The density tends to increase down the group. Melting and boiling point decrease. All right? As you go down the group, they say the atom has an extra shell, so the size of the atom becomes bigger. So the attractive forces between separate atoms work over further distances, so it's a weaker force. Do you understand? The attraction between the nucleus and the outer shells act over a greater distance, therefore the force then is going to be less. All of them lose one outer shell electron to form a +1 ion. Now when we go and look at bonding, previously we've said that all the group 1 elements have one outer shell electron, and when it comes to bonding, if it's an ionic bond, metals tend to lose that electron. If they lose an electron, they become positive. Because they lose one electron, the charge is +1. The group 2 elements will lose 2 electrons. The charge will be +2. All right. General reaction. When I have an alkali metal, remember this is a group 1 metal. The ones we commonly work with, lithium, sodium, potassium. Okay, group 1 metal. When it reacts with water, it forms a hydroxide, a water-soluble hydroxide, which is alkaline. It forms an alkaline solution and hydrogen gas. Who can remember, how do we test for hydrogen gas? Makes a whistling or popping sound. Okay, so the test for hydrogen, we have a burning splint or a lighted splint. And we hear a popping or whistling sound. Okay, and it burns with a blue flame. That is hydrogen. Remember, hydrogen is colorless, odorless, tasteless. We can't see it. But while the reaction is occurring in the test tube, I will see bubbles, effervescence. That's an indication a gas is being formed. If I catch up the gas, I will find that it is hydrogen gas. If we have a look at the reaction of lithium with water, who can remember what hydroxide looks like, the formula? Yes, it is OH. Remember, it's one of the polyatomic ions, and it's got a charge of -1. Okay, so now, when lithium metal reacts with water, what is the product going to be? Lithium hydroxide. Now, lithium has a +1 charge, hydroxide has a -1 charge, so the formula remains as it is, lithium hydroxide. Now, together with the lithium hydroxide, what are we going to get? Hydrogen gas. All right. Why do I write hydrogen gas H2? Hydrogen is diatomic. All the diatomic elements, if they occur alone as an element, it's got a footnote 2, diatomic. The next step, we have to balance this equation. Can you remember how we balance equations? Large numbers in front of the formula. Okay? So we have to start counting the atoms from left to right. Here I have 2 hydrogens. There I have 2 hydrogens. It seems to be okay. Here I have 1 oxygen. There I have 1 oxygen. There I have 1 lithium. Here I have 1 lithium. That one happens to be balanced. Oh, it's got 3 hydrogens. Sorry, I missed that. Hydrogen, we have 2 over here. Then I've got 1 and 2 over there. So how many hydrogens have I got? I've got 3 over here and I've got 2 over here. So what's the trick? I will put a 3 in front of this one and a 2 in front of that one. Okay, now count the hydrogens. Now, how many hydrogens have I got? I've got 6 hydrogens. How many oxygens have I got? 3. So let's first do okay, we get lithium hydroxide plus hydrogen. We have to balance. 2 hydrogens, we have 1 and 2 hydrogens there. So on this side I have 3 hydrogens and on this side I have 2 hydrogens. Okay, lithium I have 1, lithium I have 1. I have 1 oxygen, that seems to be okay, but we have a problem with the hydrogens. How am I going to do this? If I put a 2 in the front, how many hydrogens will I have? 4. Okay. How many oxygens will I have? 2. So, if I go and put a 2 there, now, just ignore the lithium for a moment. How many oxygens do I have? 2. Well, now it works. And how many hydrogens do I have? 2. But there I also have 2. So now I have 4 there and I have 4 over here. What happens? How many lithiums have I got? 2. So I will need 2 lithiums. All right. So to balance this equation, I will have 2 waters, 2 lithiums, 2 lithium hydroxides, and 1 hydrogen. They all lie in group 1. We said elements in the same group tend to behave similarly. Okay, same properties. So it sort of is logical that it should give you more or less the same thing. Can we do one? Can I do it? Are you with me? 2 hydrogens. Okay, hydrogen and sodium, I am going to get sodium hydroxide. Once again, sodium has 1 bonding place, hydroxide has 1 bonding place, so the formula works. Plus, I will get hydrogen gas. We have to balance. I have 2 hydrogens over there. Here, I have 3 hydrogens. So there's the problem. Let's just carry on. 1 oxygen, 1 sodium. So we have to go and have a look at the hydrogens. Once again, if I take 2 of them, I will now have 4 hydrogens, so I will need 2 over here, then I also have 4 hydrogens. But now I have 2 oxygens, but it's okay because I also have 2 oxygens there. Alright? 2 sodiums. Balanced. How would the next one look? Exactly the same. I can go and write them. I am going to get potassium hydroxide plus hydrogen. And once again, I'm going to take 2 of them, and I will get 2 of them. All right. Any questions on that? When we do balancing, we refer to something known as state symbols. What are state symbols? It means you must indicate is the substance a solid, a liquid, a gas, or water soluble. How would this look? That one is going to be a liquid. Okay? Potassium is a solid. This thing is going to be AQ because it's water soluble. And this one is going to be a gas. Alright, state symbols. Okay? If the question says, write a balanced equation, include state symbols, then you must. Okay. Right. Now that was the reaction of the alkali metals with water. Now they are going to react with oxygen. Yes. Reactions with oxygen. When anything reacts with oxygen, what is the product? An oxide. Alright? So, if we have lithium and it reacts with oxygen, the product is going to be lithium oxide. What's the formula? Lithium has a charge of +1 because it's in group 1, but oxygen lies in group 6. It's got a charge of -2. So we said, how does the formula go? Over there like that. So I am going to have Li2O as a formula. All right? Anything else? Okay. If I start off, it's going to seem like I have 1 lithium. There I have 2 lithiums. So maybe it's going to be a 2 there. But already when I look at the oxygens, I have 2 oxygens. There I only have 1 oxygen. So I am going to need 2 oxygens. So how many lithiums do I have? I have 2 times 2. I have 4 lithiums. Try the next one. Can you see that? The next one should be the same. Why? Because it's a group 1 metal and it's reacting with oxygen, so the formula is always going to be in the form of, if I do it over here, just want to rub out some of that. Over here I will get sodium oxide, Na2O. Over here I will get potassium oxide. And when I start balancing, they are all going to look like that. State symbols, lithium, the metals will be solid. The oxygen is a gas. Now this thing is a solid. We're not working in a watery medium. It might be water soluble, but we aren't working in a watery medium. So salts are solids. And that's a salt. Metal and a non-metal. So they would all be solids. All right. Next one. Now we are going to have a look at the reaction of these metals with chlorine. I just want to go back to the periodic table. Where does chlorine lie? No? When heated. What does that tell us? Does it want to react very easily? No, we have to help it along. All right. So when lithium reacts with chlorine, we are going to get something, lithium chloride. Now what's the formula going to look like? How many bonding places does lithium have? And chlorine? 1. So the formula is just lithium chloride as I've written it there. The next one. What's my product going to be? Oh, it's not yet balanced. Sorry. Okay, let's balance it. I've got 1 lithium, but I've got, why do I have 2 chlorines there? It's diatomic. Over there I only have 1, so I will need 2. But now I also have 2 lithiums. Include state symbols. Once again, we said all the metals are solids. How do I know they're solids? Yes, they are all metals. All the elements on the periodic tables are solids except mercury and bromine, which are liquids, and hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. They are gases. Okay, so they are solids. You don't have to guess, you should know. Chlorine is going to be a gas, yes. And the product that is formed is going to be a solid. Here the product is sodium chloride. Do you understand? Potassium chloride. Okay. So now we've done quite a lot. Yes, they're going to balance in exactly the same way. 2 there, 2 there, 2 there, 2 there. State symbols exactly the same. Now we've done quite a bit. Part of chemistry is being able to write and balance chemical equations. All right. Now, up until now, I think in grade 8 you learned, and grade 9 something about synthesis reactions and decomposition reactions. Do you remember? Types of chemical reactions. All right. Now we're going one step further. We have now looked at the group 1 metals. All right. And we've made them react with water. We've made them react with oxygen, and we've made them react with chlorine. Okay. So, the only one that is got something actually that you have to remember is the reaction with water because we get hydrogen plus the salt. With the others, we just get one product over there. All right. You must sort of try and order the types of reactions together, because when we're finished with grade 10 and 11 work, it's expected of you to be able to recognize an equation and write it accordingly. Okay. I can just simply, at the end, in the external exam, I can give a question, write a balanced chemical equation for the reaction of magnesium with oxygen. Now, magnesium is a group 2 element. We're still going to do them. But you must be able to know, oh, element with oxygen, we get an oxide, nothing else. There we go. All right. So, yes, always. So it's easy. Everything with chlorine is going to be a chloride. Do you understand? Everything with sulfur is going to be a sulfide. Sulfate is a polyatomic ion. Okay? Do you understand? So we change when we name these compounds. We have sodium and oxygen. I don't call it sodium oxygen. I call it sodium oxide. The ending changes to IDE. All right? Or if we have a polyatomic ion, it can be a sulfate or a nitrate or a hydroxide. Do you follow?
On the Gold Coast of West Africa lies the peaceful and diverse nation of Ghana. I'm pretty close right now to the geographical center of the Earth. It is also one of the last pockets for elephants in the wilds of West Africa.
You know, every country in the world just about has cattle, sheep, goats, horses, donkeys. But it's only Africa that has the real megafauna, the charismatic stuff which people in the rest of the world want to see.
The passion that the staff have for the job.
There's value to a bird which brings birders to a place like this. I mean, this is a birding paradise. We see an intrinsic appreciation and joy from seeing the wildlife out here, but not everybody does.
You can't get to Moli and then will not be passionate about what we do, because you'll be the only one left. Everybody is passionate.
The only worthwhile war, the war against destruction, the war against loss, the war for peace, for balance, for inclusion.
It is out of my way. Buffaloes, elephants, tigers, atreus are still in existence.
If money fails, then Ghana is without wildlife.
Join me as we journey to the untamed wilderness of northern Ghana to meet these last defenders.
The people within the law enforcement agencies don't really know you're talking about a roan antelope. Somebody thinks it's just like a goat.
Aye, 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 aye. so sad. Black man, you are on your own. Mother Africa, tell me what happened to your sacred stone. We are not living right, pretending to be happy when we're all alone. Don't care about no one, it's me, my cash, my car, and my cellular phone. The future. You've got to be a student and not just a teacher. Everybody's talking money, money, or trying to cheat, yeah. And then on Sunday, it's off to see the preacher. So tell me, my friend, how is the spirit gonna reach ya? She's a black woman. What is she gonna do? Yes, I'm a black man. And me and you are you. Black man. There's a lot more to do. Black man. Who's gonna take care of my children if I don't do? It's either freedom for all or no freedom at all. Freedom for all or no freedom at all. It's either freedom for all or no freedom at all. Either freedom for all or no freedom at all.
Sira isangu mi arroz.